the next question, question 7, compute Gauss integral. I, A, B, C is S. S is a simple, smooth, closed surface. Cosine R nu over R cube square. S is the boundary of some smooth domain. Okay, and R, what's the R? R is a vector. So this is a surface S closed. It bound a domain omega. This is our S. Then suppose ABC is here. Then the vector R, XYZ is here over the surface. The vector R is this. Okay. So we want to compute this Gauss integral. This integral is called Gauss integral. So we do some preparation. We can consider this function. Why we consider this function? Because cosine R nu. Nu is the unit normal vector. Nu is the unit normal vector. Outward normal vector over the boundary S. Okay. So this cosine, by the geometric interpretation of inner product, this is just the inner product of R and the nu divided by the norm of R, because the norm of nu is 1. Okay. So our integral I is actually S R inner product with nu. So this we want to apply R cube, because here we have an R and we also have an R squared. So altogether is R cube. Okay. So by the Divergent Theorem, this would be the integral of omega. Divergence of this. Okay, therefore we need to compute this divergence. This divergence is this F. This F is the scalar function multiplying the vector function R. So we applied the previous result on the the divergence of a scalar function multiplying a vector value function. We have a formula. To apply this formula, we need to compute the gradient of the scalar function. So we need to compute the gradient of this function. This is the scalar function. So we need to compute the partial derivative first. Therefore, this is not 3, minus 3. I have a mistake. Minus 3. Here is minus 3. Okay. So this will be minus 3 minus 4 and then dx. Okay, so this will be minus 3 minus 4. The partial derivative of this r with respect to x, we have computed this several times. We know that the result is x minus a. the norm of R. Because our R is this function. Our R is this vector valued function. So the norm of R is the square root of x minus a squared plus y minus b squared plus z minus c squared. Therefore, it is easy to see that the partial derivative of this R with respect to x is given here. Okay? So we have this result. Then, simplified this, we get minus 3 x minus a R norm of R power 5. Okay, this is the partial derivative of the function with respect to x. Similarly, you compute the partial derivative with respect to y and z, and then you will see that the gradient of this function. The gradient of this function would be minus 3 R over the norm of R 5. Okay, so having computed the gradient of this function, we can compute the divergence of our f. Why we want to compute the divergence of f? Because from this equality, we know that the integral we want to compute is the divergence of the function, divergence of f over the domain omega. Okay, therefore we need to compute the divergence of f. But if ABC is a point in omega, then R is 0 at that point. So f is singular. There is ABC is a singular point of f. F is not differentiable there. So we cannot apply the following computation. So we consider the first simple case. First, we consider the case that ABC is not in omega. ABC not in omega, then our f is smooth. F omega R3 is C1. Omega is the closed domain bounded by omega is closed domain bounded by S. Omega is closed domain bounded by S. Okay. Divergence of f is divergence of R minus 3R. So applying the formula we established in the proposition we proved before, this will be the gradient of R minus 3 inner product with R plus minus 3 divergence of the vector field R. Okay, this is the formula. And what's this? This is the gradient of R norm minus 3 is minus 3 R over R5. Okay, this formula, this result we just proved. And plus this is the gradient of R norm minus 3. And we need to inner product with R. Okay, then plus the norm of R minus 3. And the divergence of R is 3. Divergence of R equals 3. Because R is x minus a, y minus b, z minus c. The partial derivative of the component with respect to the variables are all 1. So the sum of 3, 1 is 3. So the divergence of R is 3. So the second term is just 3R norm minus 3. And the inner product of R, which R is R the norm of R square. Square cancel with the norm to the power 5, you will obtain the R norm 3. Okay, so the result is 0. The final result is 0. Because the 2R here, the inner product is R norm square. Square divided by the 5 is 3 to the power 3. So it can be cancelled with the second term in this sum. So the result is 0. Okay. So having obtained this, we can complete the computation. Our S cosine R mu over the norm cube square is R cube inner product, and then this is F. So this is just our F. Okay. So continue. So this is the divergence of F. But the divergence is 0. We just compute that the divergence is 0 at the very end of at the bottom of this page. Okay, so the result is 0. So when the point ABC does not contain in the domain omega, the Gauss integral is 0. Okay, this is the easy case. Now we consider the difficult case. The second case. ABC is the interior point of omega. So this is omega. ABC is here, and we take an epsilon positive. Such that the ball centering at ABC, which radius epsilon contained in omega. So we make a ball here, radius epsilon. Now we apply the Divergent Theorem on the domain, on this set domain. Okay, so we consider applying Divergent Theorem, that is Gauss formula, on omega removing this ball. So the on the boundary of so applying the Gauss Divergent Theorem, you need to work with the unit normal vector, and the unit normal vector on the sphere of the radius epsilon is pointed inward, pointed to the point ABC. Okay, so we see that on this ball, on this sphere, our unit normal vector is R divided by R. R divided by R point outwards, a unit vector. But because this is a sphere, the point R on the sphere, at the point R on the sphere, the normal is on the same direction of R. So you simply normalize the R, you obtain a unit normal vector. But this unit normal vector pointed out of the sphere, out of the ball B epsilon. So to be an outward normal vector of our domain omega, removing this B epsilon, we need to add a minus sign. So this is why on this sphere, nu is given by this formula. And on the sphere, the norm of R is epsilon, so this can also be written by minus R over epsilon. Okay, we need this. Now we can compute our integral. So f is say 1 omega, removing this ABC. Maybe I denoted this by epsilon. I denoted this by omega epsilon. So this is our omega epsilon. Yes. Okay, and the divergence of f is 0. This is also, we also proved before, the divergence is 0. Okay. So we obtained 0 equal the divergence of f over the domain omega epsilon. Applying the divergence theorem, this is the boundary of omega epsilon. F inner product which nu d sigma. And the boundary consists of the two parts. So this integral become the boundary of omega, that is S. S equal the boundary of omega. Okay? Plus the boundary of B epsilon. And the integral over S, this term is just the integral we want to compute. Okay, this term is precisely as before. The inner product of f, which the unit normal vector on the boundary of S, on the boundary of omega, that is S, is just the integrand in the Gauss integral. So this part can be written by cosine R nu square. And for the second part, we simply write the substituting the expression of the related function inside. So f is R over R cube. This is f. Nu is here. Nu is given here. Okay, nu is given here. So copy the nu here. That is inner product which minus R epsilon. So this is our integral I Gauss integral plus R square minus sign and R cube and epsilon. Okay, so remember this formula. I need to go to the next page. I plus 1 over epsilon R norm integral is 0. Go to the next page. 0 equal I plus R minus R cube and epsilon. Okay, we have this result. Copy to the next page. Now, this is just I plus minus the negative sign minus. So But on the sphere of radius epsilon, of course, our sphere centering at the point ABC. Okay, the R is precisely epsilon. On this boundary, that is ABC. The norm of R is precisely epsilon. Okay, so this is I minus epsilon square. So that is I minus epsilon square multiplying the area of this ball. So this is a three-dimensional ball which radius epsilon. So the area is 4 pi epsilon square. So the final result is I minus 4 pi. So I minus 4 pi is 0. The conclusion is that I equal 4 pi. Okay. So this is a very important technique. If you have a singularity, you remove an epsilon neighborhood of the singularity and applied our smooth result. For example, the divergent theorem and so on. Okay. So the purpose of this lecture is to demonstrate this important technique to you. So this is an example. Our previous example, the proof of the mean value theorem, also involving removing the neighborhood of the singularity. Okay. So we in this example, the mean value, the question 5 in the exercise, we need to work with this function, but this function has a singularity at origin. When x equal to 0, this function is not differentiable there, or even undefined there. But we remove the epsilon neighborhood of the origin. We can apply our well-known argument. Okay.